we can start. So it's a real pleasure to have Damson that will give a review to our effective field theory of the fractional quantum Hall effect. Please.
Mm-hmm. Thank you, Andrea. So I'm supposed to give review talk on effective field theory of the fractional quantum Hall effect. It is I have 2 hours, so I wonder if people like to have 1 hour and a break, or it's 2 hours. How usually you have been doing?
We have a break of 10 minutes after the first hour. So
okay.
when it's about time you feel to have a good point to stop, you stop, and then we have a small break.
Okay. Yeah.
Okay.
Just 1 second. Okay. So this talk is going to be about some work that I've recently done with my students Ishian Du, Umang Mehta, and postdoc at Brown University, Sung Nguyen, and also about I will, if there is enough time, I'm going to talk about some work that is going to appear soon. The plan of my talk will be as follows. So first, I'm going to talk about the fractional quantum Hall effect, the setup, basically the microscopic theory of the fractional quantum Hall effect, concentrating on the most non-trivial aspect of the problem, which is that electrons live on the lowest Landau level. And then I'm going to argue that the system has a certain symmetry, volume preserving diffeomorphism that can be used to construct the effective field theory. If time permits, at the end, I'm going to tell you about some new thoughts that we have about a non-commutative gauge symmetry in the theory and what kind of consequences that may bring to the effective field theory description of the fractional quantum Hall effect. If there is any question during my talk, please interrupt me at any time. So let's start. So let me remind you about the fractional quantum Hall effect. A lot of this material is probably very familiar with many of you. So in the fractional quantum Hall effect, we have electrons moving in 2 dimensions. So these are the electrons in a magnetic field B. Here's X and Y axis. And the Hamiltonian of the system is the sum of 2 terms. The first term is the kinetic energy of the particles. So let me denote capital N is the number of particles. So there's here PA minus A XA squared. That's the kinetic term. And then there is a potential energy term, sum over pairs of A and B, a potential between these particles, XA minus XB, which we would normally take it to be the Coulomb interaction. PA here is the external potential, and its curl is the magnetic field. So that's assumed to be uniform static magnetic field that thread through the whole sample. If we ignore V, as we usually do in many-body physics as the starting point of perturbation theory, setting V equal to 0, then we would have Landau level. We have a system of non-interacting electrons whose energy in a magnetic field are organized in Landau levels. So this Landau level can be drawn here like this. So here is E. The energy of these levels is 1/2 h bar omega c, 3/2 h bar omega c, etc. So n plus a half h bar omega c, where omega c is the cyclotron frequency, which is equal to EB over mc. That is the frequency that classical electron rotate in the magnetic field. So in my talk, I'm going to set c equal to 1 and then absorb E into B. So this omega c is going to be B divided by M. So that is the distance between these levels, B divided by M. Also another information that we get by solving the Schrodinger equation in the external magnetic field, that each of these Landau level has degeneracy, which I call n phi, which is nothing but the number of magnetic flux quanta going through the system. Yes. So that's what we all know. It has been known from the paper by Landau in 1930, which he solved the Schrodinger equation in a magnetic field. Now, we are going to consider the case of not only one electron in the magnetic field, but many electrons. Many electrons, we say this n electrons. And if we follow the rule of quantum statistics, if there is no interaction between the electron, we would have to fill these levels. And if the resulting state has a chemical potential mu that is between the two Landau levels, then in this case, we have the integer quantum Hall state, one integer quantum Hall effect, where the number of filled Landau level is equal to what we call nu, the filling factor. Nu here in this picture is an integer. So that is a simpler version of the quantum Hall effect. The fractional quantum Hall effect appears when we have one of the case where we have the fractional quantum Hall effect is when this filling factor nu, which is the number of electrons divided by the number of flux quanta or the number of degeneracy of a single Landau level, is less than 1. In this case, we see that this picture that we have over there give us ground state that is degenerate. In fact, it is exponentially, we have exponentially large degeneracy in the limit of large n, large number of electrons fixed nu. And so if in the case when nu is less than 1, we cannot determine the ground state based on the non-interacting Hamiltonian alone. The interaction is very important to determine the ground state. So in picture, what we have when we ignore V is that we have a lot of states, all have the same energy. So here I'm drawing it like this. This is a very large number of states of the many body system with the same energy, which then got somehow lifted, the degeneracy get lifted by the interaction. So here, when V is not equal to 0, we have a spread in the energy level. So let's talk now about two energy scale in the problems. These two energy scales, one energy scale is the distance between the Landau level, h bar omega c, that is B divided by M. Most of the time we also set h bar to be equal to 1. That is the cyclotron energy scale. The second energy scale is the Coulomb energy, the energy of the Coulomb interaction. So let me call that delta, or delta Coulomb. And that energy scale is equal to E squared divided by the average distance between the electrons. So here's my electrons, and the distance between the neighboring electrons, let me call that R. Coulomb interaction has energy E squared divided by R. Now in the limit, one of the limits that we can take is the so-called lowest Landau level limit. And that limit, I'm going to take this limit in a slightly non-standard way by taking m goes to 0 instead of as in experiment, we take b goes to infinity. So in the limit m goes to 0, we can see that the Coulomb energy is larger than is much smaller than the cyclotron energy. And the reason is that this goes to infinity in the lowest Landau level in the m goes to 0 limit, but this one remains finite. The reason it is finite is because the number of the density of states on the lowest Landau level, that is nv divided by n phi divided by the volume, is just the proportional to the magnetic field. And when we take the mass going to 0, keeping the magnetic field fixed, that energy is going to be fixed. In fact, we can just find it. Omega c is proportional to E squared 1 over R, but the distance between the Landau level, between particle on the lowest Landau level is 1 over square root of B. So that energy is E squared square root of B, and this energy, h bar omega c, is proportional to B divided by m. So in the limit when m goes to 0, this one is much larger than omega c. Another way to take this lowest Landau level limit is to take B goes to infinity, and then making use of the fact that the left side grows linearly, on the right side grows a square root of B, we can make the delta C much smaller than the cyclotron frequency. What happened in this regime? Here we have a situation where the energy between the lowest Landau level to the next Landau level is so large that in practice the states that are on the higher Landau levels are not accessible. That is, they are not excited by the interaction term in the Hamiltonian. So the situation now becomes that of typical of situation appearing in degenerate perturbation theory. That is, we have Hamiltonian that is 0 in the beginning, so non-interacting. Hamiltonian is basically 0. All these energy levels are the same, degenerate. And then we have to diagonalize the Hamiltonian projected to this sector of the Hilbert space where the non-interacting Hamiltonian is degenerate. So the problem, in fact, is that the kinetic energy is completely quenched, and all the non-trivial physics is in the potential energy. When we look at our previous expression for the Hamiltonian, sum over Ga minus A xa squared plus sum over A and B, B of xa minus xb, all that this term does is that in the limit when m goes to 0, it puts a particle on the lowest Landau level. It's a kinetic energy, so it's normally that would be a part that is large, and we develop perturbation theory over the interaction. But in our case, this interaction is essential, is the part that needs to be diagonalized. So this is the non-trivial part. Any questions so far? This is the standard way to present the physics of the fractional quantum Hall effect, but I'm going to give you a little bit a different way to look at the problem of the lowest Landau level. You can think about the lowest Landau level as non-commutative space. And that highlights a non-trivial feature of the theory. So one can do the following. Let me just stay in classical mechanics. So this point of view can be illustrated even without knowing what is quantum mechanics. So let's consider classical mechanics of a system where the Hamiltonian, let me even take just one single particle. For a single particle, let me write it's k squared over 2m plus some potential. Potential of this particle. If I have more particle, I could write potential of interaction between these particles, but here V is just a single particle potential acting on our particle. So here K is P minus AX. In the limit when m goes to 0, in order for the Hamiltonian to remain finite, we need to keep K smaller and smaller. This limit when I take m to 0, the kinetic energy is a very sharp parabola in K space, and so roughly speaking, we have in this limit m goes to 0 the constraint that K has to be equal to 0 in order for our energy to be finite, or Kx and Ky should be both 0. But we know that the Poisson bracket between Kx and Ky is non-zero. Poisson bracket is equal to the magnetic field because K has a term that's proportional to x, and the Poisson bracket of P and x is equal to 1 minus 1. And so we then find a situation in which we have constraints that do not commute with each other. And following Dirac, if we want to impose this constraint in a consistent way, we have to replace. So before taking a Kx equal, putting Kx equal 0 and Ky equal to 0 in the Hamiltonian, we have to replace Poisson bracket by the Dirac bracket. The definition of the Dirac bracket is the following. If we have two quantity A and B, the Dirac bracket between A and B is the Poisson bracket minus something that we add to it that depends on our constraints. So if we have constraints that I call Ci equal to 0, take certain construction that basically involve the inverse matrix of the Poisson brackets between the constraints and construct this what I've written here to make sure that the Dirac brackets of the constraint with physical quantity is 0. That's the way to get the correct theory after that reproduces the low energy behavior of our Hamiltonian. After doing that, we can see that in our case, the Dirac brackets between x and y become non-zero, basically because this x and y Dirac brackets has, of course, the Poisson bracket is 0. Then we have x, kx, and then the inverse matrix of kx, ky, which is non-zero, and then ky, 1. So doing this, we find that this x and y, the Dirac brackets between x and y is 1 over b, or minus 1 over b. I forget the precise sign. 1 over b is the magnetic length squared. And so this means in practice that we have a theory living in non-commutative space where the x and the y coordinates do not commute. The Hamiltonian can be written in this way. So in the lowest Landau level, we can think about our system as a system defined by the Hamiltonian, which is sum over a and b, v, sum v, and we call it v tilde, xa minus xb. Where x, a, I, and x, b, j do not commute. Epsilon I, j, delta ab, del b squared, sum I or minus I. And this v tilde is related to the, it's almost the same as the potential energy between the particles. It's v equal E squared divided by xa minus xb. Except here, we have to be careful with the ordering of operators because x no longer commute with each other. So when we write expression that involves product of x and y, you have to make sure that the ordering is unique. And there is a way. There is one can derive what is the correct rules. Basically, what happened here is that if we Fourier transform that in momentum space, then this v tilde of x, a minus xb, now both are operator, is the Fourier transform of this v back into coordinate space. So q, and here there could be a envelope factor, and then e to the iq. So this is the way one can formulate. This is this Hamiltonian contains all the information about the fractional quantum Hall effect in the limit of lowest Landau level. Any question so far to this point?
No.
No. So that introduction tells us that the fractional quantum Hall effect is a very complicated interacting problem with non-trivial physics with only one energy scale in the lowest Landau level limit, which is determined by the Coulomb interaction. No small parameter. in order to make progress,
May I ask a question?
yeah, sure.
Should we also worry about interaction with the between the electrons and the material, or that is even less important?
So when we put, you mean with the lattice, or with what is the material?
Well, I mean, here are yes. I mean, these are electrons. I mean, this is a sort of gas electrons that interact among themselves, but I guess in a material there is also the actual material where the electrons are.
So in the
impurities, or I don't know.
Yeah, impurities is one thing that we completely ignore here. The impurities are important for transport properties, but in order to, but I'm going to concentrate on properties that are not like the gap or the energy, the excitations. They are not very sensitive to the impurities. The question whether the system is gap or gapless can be asked before putting impurities in. So that is the idealization that we are going to take.
Okay, thank you.
Yeah. Okay, so the type of questions that one can ask. Since the problem is difficult, we need to find a circle of questions that that we hope can be addressed without exactly solving the problem. So one set of questions that can be asked and have been asked and addressed relate to the topological properties. Of the gap quantum Hall state. Another set of questions that one can ask here is that low energy observable physics. For a gap set, if by low energy we mean energy much less than a gap, then this second set of question goes back to the first set of question, basically. But there is as we would see, there is some subset of problems in low energy physics that do not reduce themselves to topological questions. So these refer to the nu equal 1/2, nu equal 1/4 state. So these states are gapless, and one can ask the question: what are the effective field theory? What is the theory? What is the dynamics of the low energy degrees of freedom at nu equal 1/2 and nu equal 1/4? And related to this question are the question about the state near 1/2 and 1/4, but these states are gapped. N divided by 2n plus 1 and plus 1 divided by 2n plus 1 states are called chain state, chain sequences. And here we have gapped, whose energy E goes to 0 as n goes to infinity. So roughly speaking, we can think about E as something of order 1/n, which is 1/n times the energy scale of the Coulomb interaction. And the same is for the mu equal n divided by 4n plus 1, n plus 1 divided by 4n plus 1. These are also states which supposed to form series. The n divided by 2n plus 1 state, we know they exist. Experimentally has been observed up to n of order 10. And the energy gap should go down as 1 over some power of n, say 1 over n times omega c. So we can ask the question about the dynamics at the scale. So these will be non-trivial questions, which involve still energy that is much smaller than the Coulomb energy. The presence of a small parameter in this case may allow us to build to answer the question about the low energy physics. So these would be the type of questions that we are going to talk about in this talk. What is the low energy physics of state of electrons in the high magnetic field, where the ground state is gapless, or the ground state has a very small gap? Okay, so now let me tell you about a previous theory, the Halperin Lee Reed theory. It's actually a candidate to the effective field theory of nu equal 1/2 state. So before going to this, describing this theory, maybe it's worth reminding ourselves to set a standard, the story of Landau Fermi liquid theory. So the Landau Fermi liquid theory is a theory that describes interacting fermions. For example, helium-3 liquids or electrons in metal. In both cases, we don't have a small the interactions actually is as important. The interaction energy between the fermions is as important as the kinetic energy. So the standard perturbation theory of many-body physics doesn't apply in these cases. Landau Fermi liquid theory works because we have a energy hierarchy and energy. Our energy that we are considering of the temperature is much smaller than the Fermi energy. And the ratio between the energy scale where we are interested in solving and the Fermi energy is the small parameter. Landau Fermi liquid theory was proposed by Landau as a guess in the beginning, but then it can be seen to appear, can be sort of proven, but in quote from green function method of perturbation theory. That is, to all one can show to all order in perturbation theory. We can show that the result of Landau's kinetic equation agree with resummation of perturbation theory to all order. For example, the zero sound appear as a sum of diagrams in the particle hole channel, etc., etc. In the case of the HLR theory, we have the HLR theory is basically a guess, which does not have the equivalence of the of the derivation from perturbation theory. And the reason, as we will see, that there is no small parameter, there is no adiabatic, adiabatic parameter that we can turn on, like the strength of the perturbation of the coupling constant that can be used to prove the theory. And as we will see that it's also suffered from lack of certain symmetry. So in this talk, I'm going to tell you that this problem can be corrected. And we're going to see how this can be corrected. Basically, we can write down an improved version of the so-called composite fermion theory that is consistent, I think, with all the symmetries of the problem. But it is still a guess. We still don't have a way to derive the resulting theory from the microscopic theory in a way that is as convincing as the derivation of Landau's Fermi liquid theory that one would read in HED. Any question so far? Okay, so let me tell you what is the LHR theory. So the LHR theory is the idea behind it is flux attachment. Flux attachment procedure basically say that an electron is equivalent to something that we call the composite fermion. Plus 2 fluxes. And so the resulting theory is the following. We have a Lagrangian of this composite fermion field that we call psi, that is different from the electron, psi e. And the Lagrangian of this composite fermion in the theory of offering Lee and Reed is the following. Minus 2n. The kinetic energy behind minus a half 4 pi. So this A is the some Chern-Simons field, a dynamical gauge field that imposes constraint. One of the constraints, for example, is that the magnetic field B is equal to 2 times sine degree psi. So B divided by 2 pi is equal to 2 times sine degree psi. That is, you picture each of these particles. The composite fermion carries 2 additional quanta of the magnetic field B. I think here is the sign is minus. And so the picture that we have in this theory is that we have a system of particles. Each of that carries 2 extra flux quanta in addition to the interaction with the external magnetic field B that is uniform. And taking this theory in the mean field approximation, the sum of the external magnetic field and the average magnetic field small d give us 0. And so this psi fields, zero magnetic fields, and form a Fermi liquid in, so here this is at nu equal 1/2, only at nu equal 1/2. There is a cancellation between the magnetic field and this attached flux quanta smear out over the whole space, psi form a Fermi liquid, and that explains whole host of phenomena that one can observe in nu equal 1/2, in near nu equal 1/2. Any question so far?
So, sorry, why you want to put this little a field?
Okay, so the idea of offering V and read is that is the maximalist claim. The maximalist claim is that one can derive the previous theory by working with the following procedure. So I take the electron wave function, psi, and we rewrite this electron wave function as the product of some phase factor minus dj square and a new wave function. So the claim is that this wave function is described by a theory, of these composite fermions. But now this factor means that when I take one fermion and take it around the other, we have to get additional phase that comes from to compensate this phase that I've introduced. We have introduced by hand, and that requires this to interact. Each of these, each electron of this particle interact with some Aronoff Bohm fields of other particles. Basically, this is the only phase, and that is where this Chern-Simons term appears as a way to encode this information about this Aronoff Bohm interaction of the particles between these particles. So basically here, this Chern-Simons term in the interaction in the Hamiltonian imposes the equivalence, the equality between the magnetic fields and the charge. So a charge carries, basically a charge is at the same time a solenoid. So that's their idea. So the maximalist claim is that this procedure can be done exactly.
So there is a question, sorry.
Yeah.
So can you go back to the Lagrangian for the HLR theory?
Yeah.
Yeah, so can you comment on gauge invariance?
On which invariant? Which
Gauge invariance, because the Chern-Simons level is not quantized properly.
So this,
Like,
yeah, the gauge invariance that is here. It's one can Which means that these terms actually need to be rewritten in a different way. So we have to write it as A dB with coefficient 1, that is 1 over 2 pi, plus 2 times 2 over 4 pi B dB. So if we integrate over B naively, we get A equal half of B, and we get this term. So if we are not if we are not interested in global properties, like what happened in the system on a torus, on a compact space, when the number of flux quanta going through it is odd, then we can use this naive Lagrangian. Say, for example, if you just want to compute the density correlation function of electrons, for example, should be able to just use the naive Lagrangian. Any other questions?
No.
Okay, so so this procedure looks at least one can try to follow it. There is some issue. I'm not sure if it's an issue. One issue one has to overcome is the self-interaction between particles in the resulting theory. At the first quantized level, this one we don't have self-interaction of a particle with its own flux quantum, but in this field theory, we have to be careful with the self-interaction. The more serious problems is that we don't know actually if this HLR theory encodes the correct, is the effective, is the theory that that describe the low energy, is a low energy effective field theory. Basically, what have been done with this formal procedure are identity. Basically, we just rewrite one expression as the other expression. The main approximation that is done at the end is the mean field approximation. So the assumption is that this mean field approximation is the correct approximation to get the low energy effective field theory. Let me tell you about some problems that has been known from the start, from the beginning of the HLR theory. And these problems, these old problems, I think at the end, at this moment, has been solved in a certain sense. The first problem is, in the literature, is called the energy scale problem. That is, in the HLR theory, if we follow the naive procedure that's supposed to be exact, the mass of the composite fermion is the same as the mass of the electrons, and so the energy scale is B divided by M of the composite fermion is B divided by ME. For example, the gap in mu equal 1/3 state, naively it would be 1/3 of B divided by ME. And it's clearly not a correct result, because we know that the gap in U equal 1/3 state should be equal to the Coulomb energy. So something is wrong here. The composite fermion cannot have the same. The energy scale in the problem have to be finite. This energy scale has to be finite in the limit m goes to 0. So the LHR theory does not have a valid lowest Landau level limit. So no lowest Landau level limit m goes to 0. Naive LHR theory. Second problem is the lack of particle hole symmetry.
Sorry, I have a question.
Yeah.
So I didn't understand. This HLR proposal was supposed to be valid only for nu equal to a half, or more generally for other values of nu?
So it's supposed to be valid for nu equal 1/2 and near nu equal 1/2. So when I talk about 1/3, maybe that's going a little bit beyond what can be claimed to be correct. It should maybe it should be valid for nu equal n divided by 2n plus 1. Again, this energy here is 1 divided by 2n plus 1 v over me, and that's incorrect. But there is another problem that is directly at nu equal 1/2. At nu equal 1/2, or at any nu, the 2 point is one aspect of the problem, which we will see some another way to look at the problem later on. The 2 point function of the density correlation function as a function of q and omega should behave like q to the 4th in the limit q goes to 0 and fixed omega. And LHR theory does not have these properties. It's in LHR, naive calculation gives us q squared.
I see.
I'm going to explain that in a slightly different language later on. So another problem is the lack of particle hole symmetry, and that I'm not going to tell you much more about this. It's a resolution tell us that at nu equal 1/2, the fermions have to be Dirac particles. So the composite fermion has to be Dirac composite fermion, which means that it has a Berry phase around the Fermi surface. In this talk, I'm going to concentrate on this energy scale problem. Look at this from various different perspectives, and then try to solve it. Maybe that's the time for a break.
Okay, if you want, yes. So we have a, let's say, 10 minutes break, okay? Not longer than this, okay? Okay, thank you. Just, you wait, okay? Thank you. So let's start again, okay? And please, keep going, please.
Okay. Can you hear me? Okay. Okay, so what we know from the previous discussion is that we have we know that there must be an effective field theory description of nu equal 1/2 and the filling factor near nu equal 1/2. The LHR theory has some problem. in the literature or in the folklore, people used to say it, that the problem with HLR theory is that it has no lowest Landau level projection. But in order to formulate this problem in a way that can lead to a constructive solution, it's better to formulate this problem as a lack of symmetry, because if we know what kind of symmetry is lacking in the HLR theory, we can correct this problem. So I'm going to argue that the symmetry that is lacking in the HLR theory is the lack of some higher rank symmetry. It's a lack of some higher rank conservation law. So they are lacking in. It should be present in an effective field theory. So let me tell you what these higher rank conservation laws are. Actually, there's only one conservation law. Let's write down first the these equations, which we all know should be correct. Where rho is the charge density, so it's conservation of charge. That rho is the electron density. So this equation, E1 conservation must be valid in all effective field theory of the system of describing quantum Hall effect. But there is a second law that we can write down, that is the conservation of momentum. The momentum is not conserved, but we know that the non-conservation of momentum is due to the forces acting on the system. So let me write it down. d over dt times the I, which is the momentum density, plus, so maybe let me write it with index I, j, I equal to rho I plus epsilon j b. So pi is the momentum density. And the right-hand side of this equation is simply the Lorentz force acting on elementary volume. So the momentum density in our theory is equal to m times the charge density. If the theory has Galilean invariance with just one single type of particle with momentum, with mass m, then the momentum density is m times the charge of the number current density j. So now, if we take the lowest Landau level limit, m goes to 0, then this term disappears. And we are left with these equations with no time derivative. This equation can be solved. For j, we find the following: ji is equal to rho times let me go I plus 1 over b epsilon ij b take roughly right. This is I'm not going to get all the indices right. So it's basically 1 over b times derivative of t. So this vi is epsilon ij ej divided by b, which is the drift velocity. If I put E is equal to 0, then the drift velocity is 0. So J is just simply related to the derivative, first derivative of the stress tensor T. You can put this equation back into the equation of conservation of charge. And then we get an equation which is something like this, plus 1 over B. I'm not going to get the sign right. Yes, it could be plus or minus, but roughly speaking, the equation is something like this. J plus epsilon j2 I is equal to 0. This equation we found is a conservation law that should be valid in the lowest Landau level limit. And it has a form that is quite unusual for a conservation law. It has a first time derivative and second, the derivative, it's a second order in spatial derivative. And so the claim, if we want to claim that any theory is an effective field theory capable of describing electrons, interacting electrons on the lowest Landau level, we have to get this conservation law right. It has to be present in the theory. So this conservation law is what I call a higher rank conservation law, because it's basically conservation of multiplet that consists of the density and the stress tensor that combine two different quantities that usually are not combined into a set. Charge density and the stress tensor. Usually we have charge density with the current, and the conservation is the total derivative of that tense of the Lorentz vector is 0. Here we have somewhat a non-trivial conservation law. So this conservation law has interestingly appeared in slightly different form, but basically the same, almost the same physics in works related to so-called fractons. These are not theories that describe the fractons, but theories that have that share some properties of these fractons. So the equations that we've written in previous transparency, roughly, if I suppress on the indices, look something like this, where these are the spatial derivatives, leads to a non-trivial conservation of charge. So Q over dt is 0. Conservation of dipole moment. For this, okay, that's not d over dt of this is 0. can see this. If I act d over dt over rho, I get second derivative of a stress tensor. We can do integrate by part and get 0. And it turned out that there is another conservation of integral of x squared times rho. This is also equal to 0. So in some theory of Fractional that is written down by Predko, these conservation laws are present. And we see here that our effective field theory that we have to write down for the low energy degrees of freedom has to have the properties that these quantities are conserved. So they are not conserved in LHR theory. In LHR theory, the density of the electrons is just equal to the density of the composite fermions. And these conservation laws are not present in that theory. So in particular, d over t integral x times rho e is not equal to 0. Yeah. One consequence of the higher rank conservation law is that the 2-point functions of rho as a function of omega and q behaves like q to the 4th as q goes to 0 in the limit of q goes to 0 and omega is fixed. And that's very easy to see from this equation. If we Fourier transform this, we get omega rho plus, roughly speaking, q squared, basically qi2j q squared times t equals to 0, which means rho is equal to q squared t over omega. That means rho correlation function is q to the 4th over omega squared, 2-point function of t and t. If I've been careful, there will be indices in this t, but the result is that in the limit when we take q goes to 0, this 2-point function has to be like q to the 4th. So that property has been known as the property of the lowest Landau level, and here we see that it appears naturally from the conservation law that we have. Any question so far? Okay, so
well, a naive question is if you're supposed to have dipoles in a fluid, how can you? That means the dipole have some constraint in their motion, and I don't see how this fits with the fluid picture.
well, here you can see this will appear later when we write down the effective theory. But what we have, what we can see is that this dipole from this equation, this equation tell me that a single particle, a single charge, say a plus charge, cannot move in the fluid, and that's not because if it moves, then the dipole moments of the system will change. If I have a system, everything else is keep fixed, but I want to move this charge, that would violate this conservation law. So the charge cannot move. On the other hand, a dipole consisting of a charge and an opposite charge, minus charge, this thing can move without breaking the conservation law for the dipole moment. The second equation, this equation here, allows only the dipole to move turn out that it's allowed the dipole to move only in the direction perpendicular to its dipole moment. Otherwise, this integral would change. So we will have to write a theory in which both of these conditions are valid. And these are things that you're going to impose in the system. Did I answer your question, or there is some other aspect that I missed?
Well, let's keep going, and maybe we return to this point, if you don't mind.
Okay, so let's.
Just one more question, please. How to define the statistics of the particles in that case when the particle cannot move around? Does it make sense?
These are, in order to move this particle, we have to have an external force acting on it. And so it's not that this particle cannot move, but in order to move it, we have to turn on an electric field. So if we turn on an electric field, then this particle will move with the drip velocity. So that allows to exchange the position of this particle. Defining the statistics of this charged particle in the magnetic field is has a subtlety that we have to subtract I don't know what the phase when we move a charged particle in a magnetic field. Once this is done, we can get the statistics. But I'm going to concentrate my attention on this dipole charge neutral quasi-particles. So so we have a conservation law. Usually in physics, conservation law comes from symmetry. So I'm going to formulate this conservation law in a way that is similar to other symmetries in field theory. Basically, if I have a Lagrangian, so here I imagine a Lagrangian of some fields, and that Lagrangian is coupled to a source A0. We can think about that as Lagrangian plus A0 times rho plus Gij, Tij. If there are nonlinear terms, the conservation law d rho over dt plus t equal to 0 should come out from invariance of this action with respect to some transformation. And it turned out, just going to present you the result here. The symmetry is that leads to this invariance is volume preserving diffeomorphism. Which is time dependent. Time dependent volume preserving diffs. So imagine our system is non-relativistic system, so time is absolute. So we have a system that lives in at any given time, and there is a time slice. That is a space where our system lives. And on each of these time slices, we can do coordinate transformation. Xi go to xi plus xi. Each time slice. Let's imagine doing an infinitesimal transformation. So x go to xi plus xi. Since the system is in a magnetic field, it would be better to keep the magnetic field unchanged, that requires this transformation to be volume preserving in the infinitesimal transformation. That means psi divergenceless, or psi I equal to epsilon ij and ej lambda of some parameter. And we are going to allow this lambda to be a function of space and time. Lambda is a function of both t and x. That is, we are doing volume preserving diffeomorphism with parameter that can change with time. So it turned out that one can argue that the microscopic, and that can be done at the level of the microscopic theory. So the microscopic theory of electrons on the lowest Landau level is invariant. One can show that it's invariant under the following transformation. The transformation at which Gij transform to Gij I equal epsilon ij j lambda, basically in the same way as the matrix tensor would transform, but A0 transform like this. Plus lambda naught minus square. So here I'm just insert this every square into here. Not very important. So here one can show that starting from the microscopic theory of electrons on the lowest Landau level and coupling it to the metric and to the scalar potential, one can show that the whole system is invariant in the lowest Landau level limit when we make these time-dependent volume-preserving diffeomorphism of the external source. So the invariance of the action under this transformation, so the action have to be invariant under this transformation, leads to this higher rank conservation law that we have seen before. So we can see it here, A0 transform like A0 plus 0 of lambda, and Gij roughly transform like Gij plus second derivative of lambda. So here's first derivative of xi means second derivative of lambda, and that implies the higher rank conservation law. And so after this, we know that the theory, in order to have the higher rank conservation laws, we have to ensure that our theory, whatever we are writing down, have to satisfy this conservation. Has to be invariant under this transformation. So this is a requirement on the effective field theory. And I think this requirement is basically what needed to ensure that our theory describes lowest Landau level limit.
I have a question.
Sure.
So when you say that you can prove it in the microscopic theory, you mean in the theory in which the Hamiltonian is just the Coulomb potential, but the coordinates are non-commutative? Or?
Yeah, we can do that. In fact, we can do the following. We can take the so one way to do that is to take just the theory before projecting to the lowest Landau level, an action which is integral over t and x dt minus 3, 0 psi theta 1 over 2m derivative of psi plus potential. And then observe that this action is invariant under certain diff, time dependent spatial diff. With some parameter psi a, and the and it's invariant under this time diff spatial diff plus a U1 gauge symmetry. And then observe that in the limit m goes to 0, there is this transformation has simplified, and if we limit ourselves to combination of these two that keeps, we then take combination that keeps AI invariant, that it doesn't change our magnetic field, then we get back this this invariance. But we can also show that it's the invariance of the theory just in the lowest Landau level.
Okay.
So the Coulomb interaction has to be modified. In the distance between particles has to be measured with respect to the new metric. We introduce coupling to the metric. The interaction has to be dependent on the distance of this between this particle in the new metric. Okay, so now this theory has the following. This transformation has the following properties. These transformations with parameter lambda has the properties that they do not commute. The symmetry that we have introduced here, though, looks like it has one parameter, and from the point of view of A0, it looks like the U1, almost like a U1 global symmetry, because it acts on A0 by adding lambda dot to A0, almost like U1 symmetry with parameter of the gauge transformation being lambda, but it's not a abelian symmetry as one see from this expression. In fact, one can compute and find that the two infinitesimal transformation do not commute, but becomes another infinitesimal transformation with lambda 1, lambda 2 is something like LB square epsilon I j di lambda 1 dj lambda 2. So this means that the in our theory the charge is not going to commute. Sorry. Charges do not commute. In fact, if I naively look at this, we will find that the two charges, 2 different points, has to have certain commutation relations. Looks something like this. Square. This is the long distance version of the GMP algebra. GMP in the long wave Planck limit. Okay. So if we write down a theory with this symmetry, we will find that generically our charges will not commute. That's consistent with what we expect at the lowest Landau level. When the charge or the operator of charges of electron do not just commute with each other in the before projecting to the lowest Landau level, but do not commute with each other on the project to the lowest Landau level. So now the question is how to write down a theory that is invariant under this transformation. Delta GIJ equal I, and delta A0 is lambda dot plus basically Poisson brackets of A0 is lambda psi is equal to epsilon G lambda. So it turned out that there is a general one can write down. There is a procedure to make sure that this symmetry is invariant, which probably I won't have time to go through. But there is the one feature of this is that when we write down the Lagrangian, we have this term, the Lagrangian. It's always have to be replaced by a new term. And then but correct way to write it is where V I is epsilon ij divided by B, the drip velocity, and VI is just VI. So this is needed to make the time derivative term invariant under this transformation. Under this this transformation, maybe I just ask you to take my word, and I will explain the physical consequences of these new terms. So these new terms. This new term is tell us that this if psi is psi, we take psi to be the composite fermion that was introduced in the LHR theory. This means that this composite fermion has dipole moment because it's coupled to the electric field. So there is this term can be written as electric field times the dipole moment, and the dipole moment operator is now basically the momentum operator of the composite fermion divided by B. And that means the following: that is our composite fermion. This composite fermion moving with momentum p, then it's actually a dipole with dipole moments proportional to p. So p cross z, it's p cross z divided by b. So the theory that we have written down here, if we include the if we include into the theory the dipole moment, then the symmetry is going to be to be ensured. And all the conservation laws that should be valid will be preserved in the new theory. So, the effective field theory of the new equal 1/2 state is the theory that preserves all the symmetries of the new equal 1/2 state. All the symmetries that thing I know can be written in the following way. It is a theory of Dirac composite fermion. It has to be Dirac because it's because of particle hole symmetry that I didn't have time to talk about. So it has the form of this theory is coupled to the composite to some gauge field. Then I have generic terms. We have these dipole interactions. This epsilon ij divided by d, that is the trip velocity times this 2, and then the necessary A term, I term, and that's it. That's the plus other term not fixed by symmetry.
Sorry, I have a question.
Yeah.
So if you're saying that the microscopic Hamiltonian has this infinite dimensional symmetry, so doesn't that mean that the model is integrable and that maybe you can solve it exactly in some way?
It doesn't have. It just have one single conserved charge, the density. So it doesn't have an infinite number of conserved charges. So the symmetry has one single parameter lambda.
Okay.
Yeah.
But it's like a general, I mean, it's like a gauge symmetry, right? Because this is a position dependent.
Yeah, but it's gauge in the sense that the theory is invariant when we have an external we couple the system to external potential, and we change the external potential appropriately, and then it's a gauge symmetry.
Okay. Thank you.
And the set of, if we keep this potential invariant, then we just have a finite number of conserved charges.
Okay.
Sorry, can I ask a question?
Sure.
So when you have this electric field turning on, is it going to change the volume the ring diffuse morphism symmetry?
I didn't get your question, but when I think, let me try to answer what I think is the question. When we turn on the electric field, there are the conservation laws becomes broken, but we know how broken they are. What are the right-hand side to the conservation laws? And so when we turn on external potential A0, we still have we know exactly what kind of new conservation law should be, and this will be the constraint on our theory. So the momentum, for example, has to be changed. The change in the momentum is equal to the Lorentz force. That this is just exact. So we have to satisfy this exact equation.
Thank you.
Yeah. So this again, this is the this theory with two. So compared to the LHR theory, there are two modifications. One is the direct composite fermions that make sure that particle-Hall symmetry is satisfied, and there is a dipole term. Make sure that there is High-Grand, we satisfy this High-Grand conservation law. So from these we can compute correlation functions.
And sorry, one question. So in this theory, there is no Chern-Simons term anymore. There is no flux attachment.
There is no Chern-Simons term of the form ADA. So this ADA term is absent, and it would be generated if one put these the theory in, say, put it away from 1/2, like 1/3, or in a chain state near 1/2. This ADA term is generated from the loop psi. But exactly at 1/2, this ADA term would break particle-Hall symmetry. So I just write it down here. It's actually a little bit subtle question, but it's the essence of this of the answer is that naive Chern-Simons term would break particle-Hall symmetry. It should not be there in the theory.
It's Paul. It's Paul.
Hi, Paul.
Hi. Maybe I would like to take an opportunity to ask a question about this formula, which I probably have to ask you long ago. Maybe it's an opportunity. Let's take external field. Let's remove external field from this formula. So assume that electric field simply 0.
Mm-hmm.
Is this correct that it will be only the first line remains?
Yeah, the first line remains, but the but what is the remnants of the second line is that the operator rho is the density of electrons is identified not with the density of the composite fermions, but with the following operator, with the operator that looks like epsilon ij I psi equal to j psi. So that is the what we get.
And the rho e is what is this? It's a psi dagger psi? What is rho e?
Yeah, it's the electron density. And in the identification with the operator in composite fermion theory.
That's I probably missing something. In the formula, there is no psi e, psi sub e. It's only psi.
Yeah, it's all psi. So
yes. Okay.
Psi of
So
e,
mm-hmm.
We don't know how psi and psi of e relate to each other explicitly.
Mm-hmm. But let me take take it in the face value. So I take these 3 lines, I put electric field 0. I will not put magnetic field 0 because it's a Hall effect. Then I don't know about the last term, but at least the second line vanish, and the first line remain. The last term probably A times B magnetic field.
It's just imposed a constraint on the density of psi.
Constraint of the density, right, right. Constraint of the density. Okay, yes. So the density is equal to B, maybe 1/2 B. Okay. But this small field A remains, right? Remains. Yes. So if I integrate, because the small field A comes linearly, that's basically a constraint, right? So I integrate over A, I get a certain delta function, right? So it's a constraint. So I'm looking on this constraint, and this constraint says that the current of this psi vanish. But if current of the psi vanish, the psi electrons simply do not move. But this
electron can move, but the psi cannot move. Psi cannot move, but electron
don't move. But there is no electron, so I'm taking this as a face value. Am I supposed to integrate over psi's? But then nothing remains. Theory is it's a constraint which eliminate all degrees of freedom. I never understood.
Not all the degrees of freedom, because psi psi has more than just so one way one can visualize this is that if psi form a Fermi surface, it will go 1/2 psi. So what has eliminated by the constraint are the volume. So we cannot change the volume of psi. So going this way is because B has to be equal to psi delta psi. This one also is eliminated. Make it move like that is eliminated. But what is not eliminated is a deformation of the Fermi surface that keep the volume the same and the center of mass the same. So this one is still a degree of freedom.
But it's not clear from the Lagrangian which you wrote, because Lagrangian which you wrote looks like the first line looks like simply fermions in the gauge field, which eliminates all degrees of freedom. So it's probably has to be added something or some footnotes, or I don't know what.
No, it eliminates only the total density and the total momentum density, basically, or current as the degrees of freedom. But it doesn't, because the Fermi surface has so many degrees of freedom. It cannot eliminate everything. Like in one plus one dimension, that would eliminate everything, but not in not in 2 dimensions. Because we can change the shape of this Fermi surface.
Also, you said that, but I don't see it from the first line. From the first line looks to me like no motion whatsoever, but so must be understood somehow differently, perhaps. But I have one more question. You said that psi is a composed fermions. It's good to know what composed fermion is. Maybe it's an object whose commutators psi dagger psi is not canonical like for normal fermions, maybe. But the way how Lagrangian is written, it's canonical. And so what's the difference between, that's another thing which I miss. Usually commutation relation between psi and psi dagger is incorporated in time derivative in the first term of Lagrangian in time derivative, but it looks like canonical.
Yeah.
So psi dagger psi probably 1.
No,
the way how it's written, but probably you mean something else.
No, I don't think I know the answer for the following reason. What we have here is just a theory at low energy, and when we talk about commutation relation, that means we basically insert a complete set of state in between these, and we don't have a complete set of state at low energies, and so that commutation relation that is written in the theory here is just canonical commutation relation, but this commutation relation will be modified if, say, higher term in the Lagrangian contains time derivative, and that we don't know.
Which are omitted.
Which are omitted. And we don't know how to-
Right. But probably all physics is hidden in that terms. No.
I think there is a change of perspective that we have. I've done here. That instead of thinking about the commutation relation on the Lewis-Landau level, we have reformulated it as a symmetry, as conservation laws on the Lewis-Landau level. And these two might be not the same. I think maybe the conservation law is just a subset of the constraint that the Lewis-Landau level constraint give us. So
I'm sorry. Why don't you finish your talk and maybe we continue with the discussion? Maybe you wanted to finish by saying something or summarizing.
I think, yeah, this basically is the all that I would like to say. From this Lagrangian, we can compute many quantities. The presence of the dipole term make the result consistent with the many constraints that we know should be satisfied by correlation functions on the Lewis-Landau level. So we get the correct consistent result for mu equal n divided by 2n plus 1. Theory, for example, we can compute the spectrum of the magnetoroton, the neutral excitation. We get some reasonable curve that seems to be consistent with the all the experimental and theoretical constraint. I did not have time to talk about our work that we want to finish and put on the web soon on non-commutative on the question whether non-commutative field theory is useful for quantum Hall effect. But the upshot is that the effective field theory is still this effective field theories we think is still the all that we can extract from low energy symmetry. Okay, so let me finish here. Thank you for your attention.
Thank you very much. This is a real public. Something. Do you have more questions? No, that's a clap, not a question. There was a who raised the hand? There is a question by Titus Neupert.
Yeah, thank you very much for this wonderful talk. I was curious about the whether you could comment more on the role of the lowest Landau level that, you know, one of the first things that you said in your talk is that the lowest Landau level is the most non-trivial property for the fractional quantum Hall states, and that's basically not true for any of the gapped fractional quantum Hall states, because I can construct them also in a higher Landau level, or I can construct them in a lattice model, in a Chern insulator. But for your theory, this seems to be extremely important to be in the lowest Landau level. And for instance, would you expect that that such a state could also emerge in a lattice model, for instance, where and if not, what is the role of particle-hole symmetry breaking, which is, of course, still there in the lowest Landau level by Landau level mixing and so on? Thank you.
Yeah, so here I'm the attention, we focus on the quantum Hall effect in continuum, the type of quantum Hall effect that appears in gallium arsenide or graphene, not in lattice system. We know that many of the topological properties of the quantum Hall state is preserved in lattice system, but in the continuum we have some extra physics. For example, that of the magnetorotons that we want to understand and to build effective field theory for. So these are the use of this LHR theory and the derivative of the Dirac composite fermion, the one that I presented here with the dipole term. The effect of, so one question that one thing that we assume here to be exact is the particle Hall symmetry. If we have a small breaking of particle Hall symmetry, then in the Lagrangian we have to add the mass for this Dirac fermion. That this is the most the leading term that will break particle Hall symmetry. So that leads to the fact that the 1/2 state, the very face of the composite fermion around the Fermi surface is no longer pi, but different from pi. And that presumably also something that for a new core 5/2 state. So all this, by the way, all this is valid also if we have a quantum Hall state on the next Landau level, the one higher Landau level, in the limit when the Coulomb energy is small compared to the distance between the Landau level. So in the next Landau level, we know we have a new core 5/2 state, and the nature of this state is still unclear to us, and this mass term may be important to distinguish, at least to understand the difference between the energy of the Pfaffian and anti-Pfaffian state. I'm not sure if I actually answer your question.
It says yes. So you have, yes, more question from Dimitra Karabarri.
Hi, just to clarify this, if I understood correctly, this high rank conservation loss came just from the fact that you constrain the system in the lowest Landau level. So is there more information that W infinity symmetry or UN symmetry, in fact, if you're in the lowest Landau level? Is there more? I mean, and one more thing, so for nu equals half, the extra thing is the Dirac composite fermion, because once you're on the lowest Landau level, any theory should have this high rank conservation loss. Is that right?
So the higher rank conservation law is does not require nu equal 1/2. So nu equal 1/4 or any filling factor must have this higher rank symmetry if the hierarchy between energy scale is satisfied. The W infinity algebra is an interesting question, which I'm still trying to understand. My current understanding is the following. My current is that the W infinity transformation, the operators in the W infinity algebra do not have to commute with the Hamiltonian in the general. For the general Hamiltonian, they do not commute with the Hamiltonian, and they do not lead to new conservation law. For a most general Hamiltonian, like interaction with Coulomb interaction. But this is a question I'm still trying to understand more precisely.
Yeah, in principle, it's possible to derive from W infinity not only dipole excitation, but also multiple excitations. But it's true that it's not clear that there are corresponding conserved quantities, because W infinity is not commuting with the dynamics. It's just is a sort of a spectrum generating algebra. So in general, it changes all the excited states among themselves. So. Are there more questions? Okay, so thank you very much. Let's thank the speaker again.
Thank you.
Thank you very much.